Okay, so for the simple harmonic motion experiment, I've done away with the tape measure. I don't really need that for now. What you classically have in this experiment actually is what's called a fiducial marker, something like an optical pin that you can just tape to the bottom of the mass hanger, and then a marker on maybe a retort stand kind of clamped up, so that you can see where the middle of the oscillation is. We're not going to worry about that too much to start with. I mean, we can't worry about it because we haven't got that stuff, but our oscillations are going to be very quick. We're going to time 20 of them. That'll reduce our uncertainty enough, but you might see in books this fiducial marker. So we're going to time 20 oscillations, as I've just said. So to do that, I mean, you could pull this down, but if you pull this down, you might put it down too far, and then if I put it down to here, then this spring is going to get to its kind of smallest length. So I'm actually going to do the opposite. I'm going to lift it so that the spring is closed, and then I'm going to start my timer at this point. I mean, I haven't actually got a timer because I'm using my phone to film it, but you would start your timer at this point, and then you would stop it when you counted to 20 of these oscillations. And that's what we're going to do. So we do that for 50 grams. We're then going to do that for 100 grams, do exactly the same thing. You don't have to go to all the way to where the spring is closed. It doesn't, how much we extend this doesn't make any difference to the time period. So it doesn't really matter where, if you do it to where the spring is closed when you've got the whole 300 grams on it, then you're going to have some problems, because that is going to potentially swing into the window. So you don't need to go crazy. We can just be sensible with it. So anyway, we're going to get results for the time period. So we're going to do 20 time periods, divide by 20, so we've got an average time period. So we're going to get results for a mean time period, because we're actually going to take repeats. So I'd like 20 time periods for 50 grams, and then you do 20 time periods again for 50 grams, a bit like we did with the pendulum. Then you're going to take an average, divide by 20. So a mean time period for an oscillation for each mass, going up in 50 grams, I've said, so 50, 100, 150, 200, 250, 300. Might have to fiddle around with the masses on there, especially if you've got the 100 gram hanger. You might even have to tape the 50 gram mass onto it, sorry about that. And then we are going to, instead of doing something fancy like we did in a pendulum practical, we're going to just do a normal graph here. So we're going to also want to calculate the time period squared. The units of that will be seconds squared, by the way. So on your graph, where you put your units, the units are seconds squared. And then we're going to plot a graph of time period squared against m. And that means that we should get a straight line. If you follow through with the calculations from the formula in the formula sheet, so t equals 2 pi times the square root of m over k, you should be able to work out then that our gradient will be 4 pi squared over k. So we find our gradient from our graph that we've got, and then we try and find k, because, well, 4 and pi are constant, so we find k from the gradient, and then we're going to compare it to the gradient from the force against extension graph for Hooke's law. So good luck with that, and hopefully I'd like to see when you submit this, certainly the two graphs for the Hooke's law experiment and for the SHM experiment, and a comparison with your two values of k, please. Thank you very much.